I want to define the term in a single image. Okay, this image, it really summarizes what advanced production scheduling is all about. And there are various products. This one, this screenshot is taken from Preactor, but all of them at their core have the capability to upload a number of orders that need to be processed according to specific operations, specific product routings, and all advanced production scheduling systems will then will output a schedule, which can be viewed in various ways, but it's typically viewed as a Gantt chart to begin with, detailing how production of orders is going to take place across different processes. And if this were more of a Preactor overview, I'd talk in more detail about how this data is defined and uploaded. I'd talk more about how Preactor is particularly good at creating baseline schedules, and then also how the user, the production controller, can manually modify the schedule and compare various what-if scenarios before deciding upon the schedule that he or she is going to publish to the plant floor. I'm not going to go through each of those topics in detail because there's a particular area of advanced production scheduling that I want to address. And because Preactor does it so well, that's why I want to recommend, and PMC recommends, Preactor for advanced production scheduling. When PMC implements an advanced production scheduling system, Preactor is the engine at the heart of that. It can produce those schedules based upon those inputs. I want to put Preactor in its context, however. Preactor is typically going to get a list of orders from an upstream system, an ERP system, and the ERP system is going to know a certain amount, typically knows a certain amount about the raw material availability when it sends those orders to Preactor. Okay, Preactor, upon generating a schedule and then having that schedule checked and modified and published by the production controller, will often feed that schedule back to the ERP system, and it will also feed that schedule downstream to, say, a manufacturing execution system so that people on the shop floor know what to build, when to build it, and on which particular workstations. Ideally, as this takes place, first of all, order progress is fed back to Preactor, and then information about unexpected events, such as breakdowns or other delays, that's fed back to Preactor, so that the next iteration of the schedule, can take into account all that is known about updated orders, about the most current process and on the shop floor. And what we like to talk about is how each of these deals with a separate area, where the ERP system is really about external contingencies. Those are, again, orders coming in, materials coming in from outside the company. And then at this level, you're really dealing with internal contingencies, to really get a grip on what is happening internally on the shop floor. Is everything going according to plan? And Preactor is what helps you deal with the inherent complexity of creating the plan itself. And when we're talking about scheduling the production and consumption of material intermediate materials, we're talking about a specific aspect of inherent complexity. Okay, so let's delve into the specific question a little more deeply. Now, in an ideal one-piece flow environment, material would never accumulate between operations. Okay, however, not all manufacturing environments conform to this ideal. Due to setups and other considerations, intermediate material from upstream operations often must be made in batches prior to executing downstream operations, okay? And then the intermediate material accumulates in buffers. Is this our ideal one-piece flow? No, it isn't. But does it reflect the way many facilities do operate and ultimately ought to operate? Well, sure, it does. Now, this presents a potential issue because if production control schedules too much intermediate output, then internal storage overflows upstream. And even if the storage doesn't overflow, even if the buffers and the racks can hold it, well, money gets tied up in that work in process inventory. So you don't want to schedule too much of those intermediate parts, those intermediate outputs. But if the production control doesn't schedule enough intermediate output, downstream processes will starve. And then finished products will become late, as they await the completion, of the upstream products. Often, for instance, you don't see the downstream processes necessarily sitting idle. For instance, the shop floor supervisors will say, well, what can we build today? We were going to build product X. I guess we'll build product Y instead. So you're not necessarily entirely idle. You still have some utilization, but you're not building what you wanted to build when you wanted to build it, if you don't have that sufficient intermediate output. So what's the solution? The solution can be found in Preactor's material control module. So I wanted to talk about how that fits in and becomes a viable solution for this dilemma. Here we go. Once again, I'm returning to the previous image. It's larger now. Again, we have our orders and the various operations needed to create them. And one thing I'm going to do here is isolate one specific order and see how that flows through the system, and to talk a little bit more about this example facility, what's going on here. Okay, so what I've done is I've highlighted a specific order. Okay, and what we can see is we have a company, a facility that in this department is outputting finished goods, okay? And what they do, they take what are called shells. They pull shells from supply, okay? They coat them in resin, okay? And then the resin has to cure before the completed product can ship. And, curing times vary. We have this particular in this particular scenario, you have products that can either spray their shells on what's called the auto line or what's called the manual line, okay? And for certain products, and the routing is defined that it can only go on one line or the other. Some can run on both, but this will give you the overall material flow of shell to spray to curing, and then finally out the door to ship. So what's really going on here with this supply of shells? Okay, there are each particular product uses a particular shell. Some products share shells. Others are the sole product of a single shell. And what you want to be able to do as a production controller is to get some visibility, into what is going on with these intermediate materials that are being supplied by an upstream process in your facility. Okay, and there's a couple of ways to look at that. Now, for instance, what I've done is I've highlighted a particular order. I'm highlighting a particular order, and it's order 2149. Okay, and what we can see when we highlight this order, you see this is in yellow. Well, this is the name. This is the identifier for this particular type of shell. Okay, and by taking this order-centered view, we can say, oh, well, you see, this particular batch of shells, okay, is produced. We're talking about batching operations. This batch of shells is produced and is available as of midnight on January 21st, and we can see that it's slowly depleted by a number of orders, you know, over the following 2 days. Okay, and then this particular order 01249, you know, pulls this particular shell at this particular point in time. And so what you can see here is, you know, not only has, you know, Preactor, you know, displayed the consumption pattern for these shells, but in order to display it, it had to calculate it first, and it controls you where any specific order fits with respect to this, you know, with respect to this intermediate material and the supply and consumption of this intermediate material. Preactor can also give you, rather than, you know, order-centric view, a material-centric view. So now I'm going to the next slide, which looks very similar, but you see what's changed here. You see, well, now we're focused on the input stack because we can do that. And as you can see, what's yellow here? This. Okay, now we're highlighting it, and we're taking it from the perspective, from the point in time at which these shells become available. Okay, and that becomes the focus. And then we can, you know, again, see from this point in time each of the individual orders that consume a shell. Okay, and, you know, if I wanted to, you know, I could drill down to any of these. I could see, you know, what is the cycle time for each. I could see what the customer is for each of these orders. Okay, and, you know, right away, I'm going to sort of get ahead of myself a little bit and say, you know, right away you can see that there is we can start to see some actionable intelligence begin to emerge here. Because if, for instance, you know, right now we don't see a problem. We don't see a problem because, hey, we don't, you know, we consume all the shells and we never drop below zero. Okay. But wait a minute. You know, this assumes that nothing goes wrong. This assumes that there are no unexpected internal contingencies. Okay, so a production controller might look at this and say, gee, you know, what I might need to send a signal to the guys upstream and say, look, knowing that there's potentially a certain amount of scrap that could take place here, or a certain, you know, or we may, you know, have a defective or a faulty operation here. We don't want to reach, you know, the end of the day producing product for this very important customer and have no shells. So this might lead a production controller to say, you know what, I want you to increase this batch size so that I have additional shells in reserve. Or, you know what, just create a second batch. Create a second batch to give me some reserve here that's going to become available on this day. Okay, we start to see, actionable, the possibility to not just evaluate this, but to use this as actionable intelligence. And as a matter of fact, I'm going to talk about how you might do this on a less ad hoc basis. What I just described sounds pretty ad hoc, right? Well, it doesn't have to be. In addition to calculating and displaying intermediate material consumption at the facility, Preactor APS system can be configured to prohibit scheduling of production orders after intermediate material is fully depleted. Okay, so if Preactor is configured such that, finished product simply can't be produced until intermediate material is available, what it'll do is it'll stop. It will say, you know what, you may have additional orders on January 25th or January 26th. Can't make them. Can't make them at all. I'm going to put those in my unscheduled operations because you haven't proven to me that you're going to have, that you haven't proven to me that you've got available shells, available intermediate material. I'm going to flag these, at which point the production controller can look at it and tell the upstream department, okay, the proof is right here. I absolutely need you to, produce more of those shells, or I am going to have a situation in which I either have to stop my production or reshuffle my production. So that is one configuration option to prohibit scheduling of production orders after intermediate material is fully depleted. Now another option is to automatically generate supply orders after intermediate material is partially depleted. Okay, so and this is part of how PMC configures not just Preactor itself, but the surrounding system. Okay, so that if Preactor can automatically generate those supply orders, and then send them to the upstream department, then there's minimal need for that human intervention, that human dialogue. What do we do? How much do we make? Because the overall system can be configured to say, look, when those raw materials are partially depleted below a certain threshold, I've got a rule that tells the upstream department, okay, create a batch of a certain size. Okay, and it doesn't become a whole conversation. It's simply a rule that is baked in. Okay, so again, that's a lot less ad hoc than squinting at a green line with yellow dots and saying, I might have a decision point. This is something that can be automated. And then another option is none of the above. Another option is none of the above. And to simply say, for the time being, in phase one of our Preactor deployment, we are going to monitor this, but we're not going to do either. Maybe that's because there's other aspects of Preactor that we really want to prove out first, okay, because we're more concerned with Preactor creating a good baseline schedule than with Preactor alerting us to material shortages. Or maybe, the organization says this is pretty important, but that upstream department, they're a little bit skeptical of Preactor. So until the downstream department, is using it for a few months, and until they have really demonstrated, yeah, this is a system that we have confidence in. Until that happens, we're not going to extend the functionality, and we're not going to configure either of these. So you have a lot of options. Once you're calculating and displaying intermediate material consumption at the facility, you have a lot of options. Preactor and PMC together as your configurators give you a number of ways to proceed.